Consider, for example, an oil pipeline network represented into this figure. And so you have directed arcs. And in this case, the weights of the arcs describe the capacity of this arc. In particular, of our example, it would be the amount of oil that we can send per hour, say in thousands of barrels per hour. Then this means that the most we can send from node 1 to node 2 in 1 hour, it would 1000 barrels. And the most we can send from node 2 to node 4 in 1 hour would 4000 barrels, and so on. We can see that there is a specially designated node here marked by S and another node marked by T in this network. So the node 1 marked by S is equal to source, and node 6 marked by T is equal to sink. And our goal is to push as much oil as possible through this pipeline per hour from node 1 to node 6, or from source to sink. In this problem can be stated as a maximum flow problem in a directed capacitated network. So we have this network G given by the set of node N and the set of arcs A. And we arcs capacity that will denote by Uij is for every arc Ij belongs into A. U52 is given by 2. If we want to determine the maximum possible amount of the flow that we can send from source to sink so that no arc's capacity violated. For example, we can send 1 unit of flow to the path from 1 to 2, 2 to 4, 4 to 6. We can say that we don't violate any capacity constraints in this route. And so 1 to 3, 3 to 5, 5 to 6, we don't violate any capacity in this route also. Let's first develop a linear programming formulation for our problem. Our decision consists in decide how much of the flow we are going to send through every arc. So it makes sense to define our decision variables. Accordingly, denote by xij the flow through the arc ij, and introduce decision variables for every single arc on a network. And of course, the flow must be at least to 0 at most, and at most the capacity of the corresponding arc. So we have xij are all between 0 and uij. So we have one decision variables for every arc in the network. So this number we need to make sure that all the flows come out to this source. Then map and remain of any of these intermediate nodes, and all flows arrives into node T. The fourth of intermediate nodes, we can write down what we call observation flow constraints. We need to make sure that the amount of flows comes in of the intermediate nodes is equal to amount of flows comes out to the intermediate nodes. So let's write the conservational flow constraints for each nodes. First, we have XTS, our artificial amount of our artificial arc from source to sink. So we have 2 outgoing arcs to deliver. XTS is equals to X12 plus X13. Our node 1 deliver node 1 to 2 outgoing arcs. So our second conservation flow constraints are node 2. We receive 1 and we send 2 to 4 and 2 to 3. So X12 is equals to X23 plus X24. Our third conservation flow constraints is we receive 2 and we send 1. So x13 plus x23 is equals to x35. So our fourth conservation flow constraints is we receive 2 and we send 4 to 6. So x24 plus x54 equals to x4 6. So our fifth conservation flow constraints is we receive 1 x35 equals to x52 plus x54 plus x56. So our last conservation flow constraints is we receive 2 x46 plus x56 equals to xts, or artificial amount of artificial arc, denoted by x61, or the artificial arc flow. So the objective function is to maximize the total flow, given exactly as xts. So in this case, we are maximizing xts, our artificial flow. We return from sink to source. And then we have the conservation flow constraints of every node I in a network. And instead of A, we are using A prime. This is because we need to take in count in this artificial arc. So A prime consists A in the artificial arc TS. This way we can write all the conservational flow constraints in one line instead of looking at ST separately. And the conservational flow constraint states that all the inflows into I are the same, the outflows for I. So this is the amount comes into I, and this is the amount leaves I. These two amounts are equal or the same. The difference is equal to 0. And finally, we have bound constraints, or the capacity constraints, for every variable except for the variable for splendid of our artificial arc. So this is the summarize of our LP model of maximum flow problem.